Math 265A, Quest to College. I'm Joe Vasta, and we are covering our last section for the semester, which is 6.1, Velocity and Net Change. Now, the thing about this is we've been doing velocity problems every time we do one of the bug handouts. So you're not going to get that many homework problems in 6.1, and a few of them will be like things that you see in the bug handouts. So what I'm going to do before I actually do a few of the newer examples is review what we've done with a bug on a number line. So this kind of describes a bug on a number line. And this is his position function. And we find that if we take the derivative, we end up getting the velocity function. We also took the derivative of the velocity and got the acceleration. Now, when you start off with the velocity function, you take the derivative, you get a whole family of functions, negative t squared plus 2t plus a constant. And this is just one of the family members. So the antiderivative gets you back. We've asked some questions like displacement, things like that. So if you were going to find the displacement of the bug on a time interval, let's take a look at this. I've got some pictures here. So the displacement of the bug on the number line just tells you, okay, so at 0 seconds he's somewhere, and at 3 seconds he's somewhere else. And here is the position function. It's a parabola. I've kind of whited out the part that's outside this time interval. And the displacement really is the displacement as this bug is traveling. Yeah, he's traveling on a number line, but you can think of the y-axis or the s-axis as the number line. He goes 1 to the right or 1 in a positive direction and 4 down. And his displacement then is -3 feet. Now, from the angle of velocity, the displacement is gotten by doing the definite integral from 0 to 3 of the velocity function, and it is the net area. Another common question that's asked is the average velocity, which is really just the displacement divided by the time. We've been saying that from the beginning. And so here's average velocity. Here's the displacement, which is, you know, you could either write it as s of 3 minus s of 0, or it is the definite integral. And then it's divided by the time, 3 minus 0, or 1 over 3 minus 0. And it ends up being -1 feet per second. That's the average velocity. In terms of the position function, it's really the slope of the secant line connecting the points that are at that are at t equals 0 and t equals 3. And the slope of that is -1, as you can see. In terms of the velocity graph, the average velocity happens to just be the average altitude of the graph, and in this case the graph is a line segment on the interval 0 to 3. Another common question that's asked, or that was asked in this class, is the total distance traveled. Well, the total distance traveled is really gotten by taking the integral of the absolute value of the velocity. Or when we just had the position function, we did the displacement. We had to find our rest times. Our rest times happen to be, where the tangent is 0. The tangent line is 0. So we end up getting 5 feet. And in terms of the graph, the s-axis is really the number line the bug is walking on. He goes 1 to the right or 1 up and then 4 down, which gives you a total of 5 feet for the total distance traveled. In terms of the velocity graph, the total distance traveled is the total area, 4 plus 1. Another question that was asked when we studied bugs is the instantaneous velocity, which we would just call the velocity. So the velocity at t equals 0, you would just find the velocity function by taking the derivative, which is that guy, and then putting 0 in there, and we get 2 feet per second. Well, 2 represents the slope of the tangent. And if you're looking at the velocity graph, the instantaneous velocity is just the y value when you're considering t on the x-axis, or the t-axis. T is 0, the y value is 2. The last thing that I want to look at, and I just wanted to put these side by side, and that's what I'm doing, is the rest time. And the rest time is when the velocity is actually equal to 0. Now, we would have to compute the rest time if we were given the position function and wanted to find the total distance traveled. So we had that earlier. So the rest time for your position function is when the slope of the tangent is 0, which happens to be at time 1. So the rest time, I don't even know if the rest time, we didn't put this down. This is t equals 1 second. That's the answer. And so in terms of the position function, it's when the slope of the tangent is 0, and then in terms of the velocity function, it is the t-intercept. I've also assigned 6 problems that are, maybe a little bit weirder, like the 2 that I'm going to do. So I will do 2 problems. And they look kind of like your homework problems. The velocity in miles per hour of a jogger is given by this velocity function for t between 0 and 4. Assume s of 0 is 0 and t is hours. So the first thing to realize is this jogger, right when they begin, they are going 4 miles per hour, which is pretty good. But by the time they reach the end of hour 1, okay, so when time is 1, then this is going to be 4 over 1 plus 1. That's 4 over 2, so that's 2 miles per hour they are jogging, which is slower. Why? Maybe because they're getting worn out. So this function models that, and they say determine the position function. So look, here's velocity. We want position. So what are we going to do? We are going to integrate v of t to get the position function. So let's go ahead and do that. So the position function we'll call s of t. I'm going to integrate that. Okay. And bring the 4 outside. I'm going to eyeball this one, okay? I know we talked about the eyeball method. The derivative of that bottom of the denominator is 1. I see it on top, so that's going to disappear with that. If you were going to do u substitution, you would let u equal t minus 1, du equals dt. So when it has all been settled, you end up getting 4 times the ln of the absolute value t plus 1, and then we have plus c. Now we can keep the absolute value there, but we know the time is between 0 and 4, so we don't need the absolute value on that log. So s of t is 4 times the ln t plus 1 plus c. Now we don't know what c is, but they give us s of 0 equals 0. Okay, so I'm going to go ahead and put 0 in, and we end up getting 4 times the ln of 0 plus 1, so that's the ln of 1 plus c. So look what c equals. c is, 0. So what are we going to do about that? Well, we're going to finish this first question. It asked me to determine the position function. The position function is this guy right here, 4 ln t plus 1, and c is 0. So that is the answer to part A. Now your book, this is a warning, your book's going to say, oh, we're going to rephrase the fundamental theorem of calculus, and they're going to do things in a way that may confuse you. So just maybe rely more on these lectures if this is making sense. We have to do part B. Part B says, what is the distance traveled by the jogger in the first 30 minutes? Well, this is the distance function, which will tell me how far it was. Now I should really be looking at a total distance traveled, but in terms of this problem, we're never going in the negative direction. Okay, so we're always, the velocity, if you look at this, is always above the t-axis when t is positive. Okay, so what I'm going to do is then I'm just going to go ahead and plug in. Now a lot of people would say, hey, we'll just plug 30 into there. Remember that t is measured in hours. So we're not going to put 30 in there, but we're going to put 0.5. So S of 0.5 equals 4 times the ln of 0.5, excuse me, plus 1, which is the ln of 1.5. So let's go ahead and see what that is. This is 4 times the ln of 1.5, and I will round my answer. So it looks like, it says, what is the distance traveled by the jogger in the first 30 minutes? It's going to be 1.62 miles. Okay, so that completes the first problem. You'll get 3 problems that are kind of like this. Let's go ahead and do the second problem. The second problem says the population of a community of wildcats excuse me, is observed to fluctuate on a 6-year cycle due to variations of the availability of prey. When population measurements began, t equals 0, the population was 45 wildcats. The growth rate in units of wildcats per year was observed to be, so this is the rate, okay? Kind of like it's the velocity, but we're not going to call it the velocity. This is the growth rate. They're going to ask you to find the original function, p of t, and look, you've got the derivative, so maybe you know what to do. And then it says, what is the population 4 years later from this time? 8 years later. So let's go ahead and find out what the antiderivative of this is. So we're going to go like this, the antiderivative of 2 plus 15, and then that's quite an argument for that cosine. So let's write this out here. So 2 plus 15 cosine pi t over 3 dt. Okay, so what is this? This is the integral of 2 dt plus 15 times the integral of the cosine pi thirds t dt. Now, if you're going to do a u substitution on this, you would let u equal that. Okay, and you would go ahead and continue to work on the problem. I'm going to go ahead and eyeball this one. So how am I going to do this? Move this over here. Say, well, what is the integral of 2? The integral of 2, so this is p of t equals 2t, so that's what I got for that one. And I'm going to eyeball this and I'm going to say, well, what is the derivative of pi over 3t? The derivative is pi over 3. I'm going to go ahead and put a pi over 3 right here. This is me doing the u substitution. But I can't just go around doing that. I have to balance the books by putting maybe one out here. So it's going to say 3 over pi. And the u substitution is really reverse chain rule. So I'm going to write this as, that means the pi over 3 on the inside is going to disappear with the dt. This is just the way I do u substitutions when it's a quick one. So watch this. So this is 45 over pi. The antiderivative of cosine of something is sine something. It's a positive, so sine of this something, pi t over 3 plus c. If you'd like to do a U substitution, don't let me stop you, and you'll end up getting the same answer. Now notice what it says, and I think you can still see it here. It says T is 0, the population was 45. So T is 0. The population was 45 wildcats. So the reason they're giving us that, that's an initial condition. We plug it back in there so we can figure out what C is. So let's go ahead and do that. We have 45 equals 2 times 0. Sine of 0 times pi over 3, sine of 0, that's going to be 0. Looks like C is 45. Okay, so what do we have here? We have for answer A, because answer A said find P of T, that's what we're going to find. P of T is just this right here, 2T plus 45 over pi sine pi t over 3 plus 45. Okay, so that's the answer to part A. Now part B asks us, what is the population 4 years later, 8 years later? Now we're just putting 4 and 8 into this function. Now it's funny because if you read the original problem, it says the population of wildcats is observed to fluctuate on a 6-year cycle. So that means the population is not, it may go down sometimes and then go up, but it kind of cycles, and maybe it's on an upward spiral or whatever. Let's see what happens when we put 4 into this. Now when you put 4 into this function here, make sure your calculator is in radians. If not, you're going to burn yourself. Okay, so make sure your calculator is in radians. And when I did that, I'm going to round to the nearest wildcat. Okay, I don't want to like start chopping them up. After 4 years, this model says there will be 41 wildcats. So, wow. That's kind of funny because we started off with 45. But watch this. They said, okay, we'll figure out what happens in 8 years. And in 8 years, I plug that in there and I round it to the nearest wildcat. I got 73 wildcats. And you could plot this on one of the plotting programs, graphing programs on the computer, Desmos or whatever, and you'll find that like by the 8 years, I don't think it's going to dip back down into the 40s anymore. It's kind of like, it's like a sine wave, but it has some other things to it. It has this 2t, so it's going to be kind of like wiggling, but it's going to be wiggling its way up. And sometimes, sometimes it may drop below 73, but it's going to be on an upward wiggle. And sometimes that's what happens when you have studying population and there are variations in the availability of prey. And of course, these things are very hard to model because there are lots of factors. So this is the very last of the new material. You've got a few problems, not a whole bunch of problems in 6.1. Do your homework. Have a good day.